can match my calculations as well.
2.9 million.
2.9 milligrams. Right?
So with what happened with that 1.4, is that just like specifically for this gate or for this type of configuration, or was that just a coincidence?
Say it again.
So you know how like it just so happens to be that it's negative 1.4 for all the cases? Is that just for this specific gate, or is that just a coincidence?
You have to do the circuit analysis. I mean, every gate is different. So for this particular problem, when you do the circuit analysis, as I draw that, with both transistors you have the same voltage, and with one transistor you have the same voltage. You should be able to do the circuit analysis where the current is going, which transistor is off and which transistor is on. That's how you get the voltage. I cannot give you like one answer that this node is sitting at negative 1.4 volts always. No, that's not true. So if, let's say, Q2 is on, right? If Q2 is on, in that case, all these two transistors, Q1A and Q1B, they are off, right? Now the current in this branch is determined by this transistor, right? So now this is on, the voltage here is 0.7. So in that case, your VE will be negative 1.15 volts minus 0.7. So that is not minus 1.4 volts. You see what I'm doing here? Okay. So it depends on which transistor is on. But for this case specifically, for these three cases, it comes out to be negative 1.4 volts. Yes.
So when either of the input is 0, we are just assuming that Q2 is off, right?
We are not assuming, we proved it. We proved it in our lecture. We proved it using the equations, where we said, let's say, if your voltage is, okay, in a single inverter case, right? I'm gonna erase this transistor for a second. Getting back to the basics again, but I do want to cover all 4 problems, so it will be quick. So what we did, we said we have a reference voltage, 2 transistors, same configuration, they are equal, their saturation currents are equal, okay. So if the voltage here is just 100 millivolts higher than this one, all of the current, this is a bias current, right, flows through this branch. And you can prove it using those equations, remember? IC is ISE to the VBE over VB. You remember that? So if all of the current is flowing through this branch, this transistor is on and this transistor is off. You can assume this is on, do the analysis, and then you can prove later, okay, this is the base emitter voltage that I had assumed. But what's the base collector voltage? That's negative, so it's in forward activation. Okay, we did that in our first lecture. Yes.
Even if it's like slightly higher.
For each case, it's different, but approximately you can take 100 millivolts difference is good approximation. In the book, if you look at the design that they have, they are using a 75 millivolts difference, and they also derive the equations with rigorous maths to get the exact VIL and VH based on what your reference voltage is. Okay. But yeah, we didn't assume it is true. Yes.
Is VIH in this situation negative 0.7 because that's the amount of voltage you need to apply to any of the inputs in order for it to turn on either one of the transistors, or can you explain why VIH is negative 0.7, or is that just a given?
Okay. What's the minimum voltage that I need here in order for me to consider that logic high? Say it again?
It's the minimum voltage required to turn on the transistor, right? Or it's 100 millivolts, give or take.
Yes, so it's
More.
plus 100 millivolts.
Yeah.
That's going to be negative 1.05 volts.
Yeah.
Okay. But the problem here is in ECL, your logics are not clearly defined. So these values are given. Okay. So I shouldn't write VIH because that's the minimum voltage, because VIH is negative 1.4 volts. But let's say your high voltage at the input is negative 0.7 volts, right? Actually, you know what, the way you can look at it, when you do the TTL analysis, right?
Yeah.
Your logics are clearly defined, 0 to 5 volts.
Yeah.
So if you want to just look at the circuit and analyze it, what do you do? Okay, logic low, let's just apply 0 volts at the input, what's my output? Let's just apply 5 volts at the input, what is my output? So those, 5 volts is equivalent to negative 0.7 volts in ECL. Okay, and this is the limit actually. You remember that when you, let me just draw that diagram. I was hoping that you guys will review this on your own. Do you remember this?
Yeah.
Right? This is your V reference, right? And what is this voltage? VIH, and this is VIL. Now, if you keep increasing your VIH, what's gonna happen? Anybody remember? Exam is tomorrow.
It goes into saturation.
Yes, you're going into saturation. Very good. So there is a limit, upper limit here. And what's that limit? Either you draw these curves and find out what those limits are and see where transistor gets into the saturation region, or this value will be provided to you right here. Okay? So it's, you see how it is negative 0.7 volts. So if you kind of have, if you go beyond negative 0.7 volts, your transistor is going to get into the saturation region. Now, what's my V minimum, right? There should be like some limit for the negative voltage as well. That is based on the noise margin here. You want to have a symmetrical noise margins, right? So in order for you to have a symmetrical noise margin, you have this difference. You subtract it from VIL, then you get that defined logic low. Okay? Alright, so I'm getting back to the problem. You guys follow this now? So, this was logic high. Okay, so we have to find the power dissipation in this gate for logic 0 at the output. We need this current and we need this current, right? Right here. We found IEE, now we need, I'm gonna call this IR. Okay, now for this, we need this voltage, right? If you can recall from your lecture, I said if VOL is not given, then you have to first calculate VOL in order for you to calculate IRE. So how do we get VOL? That's our next step. Yes.
One question to answer.
Yes. Yeah. Go ahead. Go ahead.
So you do from 0 minus IE times 300, because that's like on, and then you do minus 0.7 because it drops.
Yes. That's, you have the current, so you can get VO1 easily, and then subtract 0.7. But there is an assumption that we have to make. What's that assumption again? Yes, we are ignoring Ag3. Okay. Now, Q1A and Q1B on, or Q1A is off and Q1B is on, or either case. So what's gonna happen? Your current through this branch. Which branch? This one. 300. If I assume one transistor on. If both transistor on. You know that current will be the same, right? Ignoring the base current. Okay. So if we ignore the base current, what's the current here then?
IE.
Yes. So I'm gonna call this as IC1. So IC1 approximately IEE, that is 2.9 milliamps. Okay. Now if that's the current, we can get VO1. So VO1, which we need to get VOL because that is not provided to us. So VO1 would be simply 0 minus IC1 times 300, right? Make sense?
Professor, could you write a little bigger, please?
Okay. So what's the voltage here? That's going to be minus 0.870 volts. Is that correct?
Yeah.
Okay. Now VOL, what is VOL? So this goes to, now this Q1A, Q1B, if that's what I'm using. This is Q3, this guy is off, Q2. Right? We don't have to worry about it. So here you have resistor 2K. Now we have found this voltage, which is negative 0.870 volts. Now it's easy to find V naught, right? Because this transistor is always in forward active region. This base emitter junction is 0.7 volts. So this is 0.870 minus 0.7. That's going to give you 0.7 minus 1.570 volts. 75% of the problem is solved. Okay. Now, can you get the current here? So IRE, what is IRE? Minus 1.570 volts. This node is sitting at minus 1.570 volts, right? That's going to be minus 5 divided by 2. Good. So that's going to give you a current that is, in my notes, I calculated this as 1.715 milliamps. Good. Now all we need now is I total. What is I total? Sum of these two currents. So that's 2.9 plus 1.715. That's going to be 4.615 milliamps. Now 95% of the problem is solved. Okay. So what's the power dissipation now? That's 4.615 milliamps times 5. That's gonna give you 23.1 milliwatts. That's your answer. Good? Yes.
Would you use the same process for a Wash
Yes, same process. Same process for OR gate as well. And I think we did OR gate in the class for logic 0, right? Yeah, that's okay. Power dissipation here, looking at a magnitude.
Just make sure in ECL, either Q1 or Q2 are on, right? Not both of them are. Never, right?
If the Q2 one, either Q2 or Q1,
Yeah, they can't both go on right?
In the transition region, maybe that's possible. You see that transition region? But we don't want to be there. That's like forbidden region. No, otherwise only one is on. Yep. Okay, good. Any questions? Let me look at the time. I have 3 more problems. Can I move on to the next one? Okay. Right. I'm gonna do TTL NAND gate first. Okay. You guys say that it's kind of not clear this point because of the reflection, right?
Can you stick to the right side, please?
Alright, TTL NAND gate. So this circuit diagram is given. This you should know by heart. So the problem that you have to find out is, first point, find VIL and VIH. Find fan out 1 for worst case input requirement. Not sync. I don't want to use this. Source. And given beta F 20, beta R 0.5, beta L 1, VCE sat 0.2 volts, VD on equals VBE on equals 0.7. VBE and you have to find this for noise margin of 150 milliohms. So that's the problem. Okay. Now first, let's just call this A and B. Now what happens when both of the inputs are low?
And that first transistor is in reverse active. It's although current goes through there.
Reverse active?
Yeah.
On.
Oh, on and saturated.
Let me just go over this again. Let's say this is Q, okay? This is your base collector, this is your emitter. Now for forward active region, VC is higher than VE, okay? And this is IC, this is IE. And what is IC? Beta forward, IB. And what is IE? Beta forward plus 1, IB. You know how you get this? Basically, IE is the sum of IC plus IB. Since IC is beta of IB, you factor out IB and then you get this expression. Now, what if your emitter is at higher, voltage as compared to the collector? So this is your normal forward active region. Now, if your emitter is at higher voltage than collector, I'm drawing the same transistor. So here VE is greater than VC. So I'm gonna flip the transistor and redraw this like this. This is C. This is E. And this is I. You guys follow this? I flip this transistor like this. So emitter goes up, collector comes down, right? Now since the emitter is at higher voltage than the collector, right? It's your reverse active region, means emitter acts as a collector and collector acts as an emitter. Now in this case, if you want to find out this current, well, the gain associated with this kind of circuit is that's beta R. It's very, very small because the construction of the BJT is such, this is beta R, right? Much less than beta R. Now if you want to get this current, which is IE of the original transistor, equals to the collector current, acting collector current of this transistor, that's going to be No. Okay, so let me just, I don't want you guys to make this mistake. All right, look what's happening. This is the emitter, okay? So let's just do this. This is the emitter, since it's at higher potential than the collector. So this is acting as a collector, okay? So this guy over here is acting as an emitter. So I'm gonna delete the old designations. Because now this is your collector, this is your emitter. So when you delete the old designation, now it's clear to you this is IC, which is related to IB through beta R. So what is this IC now?
Beta RIB.
Beta RI. Okay, and what is IE?
Beta R plus 1.
Beta R plus 1 IB. Yes.
So, in terms of the first transistor you drew, it would be so those equations aren't, so that C and E aren't referring to the first drawing, they're referring to the second one, right?
Because they're functions of
Say it again.
No.
No. This is related to this transistor.
Okay.
I flipped this. I said, okay, it's the same transistor. Since VE is greater than VC, I want to put the terminal on the top, which is at high potential. So I flipped it. So when I flipped it upside down, this becomes my emitter, this becomes my collector, right? But since emitter is sitting at a higher potential than collector, so it acts as a collector. That's why I have collector in parenthesis. And this collector is acting as an emitter. Okay? So now this new collector is related to IB through beta R as beta RIB. Same expression that we had for this actual transistor. You guys follow that? Yes.
So how about the base? Like voltage wise, is it positive or negative with relation to C or E? Or?
This is positive.
So B is always positive in, as it relates to C and E.
What's the conditions for the forward active region? VB is forward bias and DC is reverse bias.
So current is practically 0.
So here it's opposite. I don't want to write that down because we are only dealing with the currents. It's gonna just confuse you. Okay. Now why am I doing this? Because we are giving an input at the emitter of that Q1. Okay, so that's either gonna be in saturation region or it's gonna be in reverse active region. When will this be in reverse active region? Because when the emitter is at higher potential than the collector. So when emitter is at a higher potential than the collector, it's gonna act as a collector. Everyone with me? Okay. So now let's get back to the TTL 98. So when both are low, right, the current follows this path, right? Right? And this transistor is on and in saturation region. It's gonna try to pull out the current through the base of Q2, turning this transistor off. This transistor off, no current flows here. 0 volts, turning this transistor off. Okay? And all of the current flows into the base of Q4, turning Q4 on, and the current flows. I have an output here. Since this is on, so the current is gonna flow this way. You're gonna have B naught as output high or low. It's gonna pull it up to a logic high. This is your pull up circuit. This is your pull down circuit. Okay, so we did when both of them are low. So you have logic 1. What happens if one of them is low?
So current going.
Still the same configuration, right? Because if this is high, this diode is reverse biased. The current here, I have 2 path here, right? So if you pull this up, this is reverse biased, open, then all of the current will flow through this direction, right? Still, right? So this transistor is off, and voltage V0 is gonna pulled up to the logic high. So when either one of the inputs are 0, your logic is high. Now what happens when both of the inputs are at logic high?
Q1 goes into reverse active.
Yes. See, this is your, in the exam, just label this as an emitter first and collector first. And when you say logic high at the input, you know it's acting as a collector. And this is acting as an emitter. Leave these old designations. This is your new collector, this is your new emitter. Okay? This is your reverse active region. Okay. Now, I'm going to talk about the worst condition as well, let's look at this. You said I cannot go here. Let me just put this up. Sorry, I'm not used to this.
Yeah. Super
So we are interested in logic high, right? So we are interested in logic high, right? We have to find N1. Okay, and first, can we quickly find out VIL and VIH? Give me the value of VIL. 0.8, yes, but how?
Negative 0.2 plus 0.5 plus 0.5.
So one of them is low, right? It's gonna turn this off and this off. So 0.5 here, 0.5 here, 0.2 here, right? Because this is in saturation region. So that's 1 minus 0.2, that's gonna be 0.8, right? So your VIL is 0.8. What about VIH? For VIH, now this is reverse biased. We need a maximum voltage here, right? What's the maximum voltage that we can have here? 0.5. And this is forward bias, right? Base emitter, 0.7. This is 0.7 on, this is 0.7. So 0.7, 0.7, 0.7. This base is sitting at 2.1. So input will be 2.1 minus 0.5. That's going to give you 1.6 volts. I'm sure you guys know this very well, right? Okay. So let's get to the main topic. So noise margin high. For worst case, IIH requirement. So N1 is I naught available and IIH required. Right? If it's low, then that I naught available, that's going to be divided by IIL required, right? Now let's focus on IIH first. The input required current, I not available, I'm not worried about, that's easy to get, calculate. Now you have this first gate right here. I want you to understand this. Now you're feeding n number of gates here. Now the question is, what is the worst case for IIH? Now if you look at the inputs, right, A, B, for V output high, you have three cases, 1, 2, 3. So at the output, you can have sorry, I want to write this one too. So for input IH high, a high, so A, B, I have three cases, 0, 1, 1, 0 or 1, 1. Right, 0, 0 we don't have to consider that because that is related to IIL, right? So out of 3, I want to find out what is my worst input high current, right? I can have transistors like this, the input transistor. One is connected here and one is 0. I can have a transistor, they both are connected to, logic high. This is logic high, right? 1. So we have to find out whether this gives you IIH worst. And when I say worst, what does that mean? Maximum current, right? So you have two cases here. This is basically a one case. Either A is 0 or B is 0. This is actually one case, right? Either one of the input is high. So either you are feeding gates like this, where one input is grounded, or you are feeding gates like this, where both of the inputs are at high. You see what I'm saying? So the question is, you have, I'm gonna just label this IIH case 1, and I'm gonna label this IIH case 2. Remember, I'm only looking at the current going in just one input, not in both inputs. Yes, it is feeding both inputs. If I have n number of gates, then I'm gonna have 2n number of inputs. But what is my current in a single input, right? Now the question is this is case 1 is high, or case 2 is high? Are you guys with me on this?
Wait, so case 1 is only one of them's on, case 2 is both of them are
Yes,
high.
you can have anything at the output, right? Maybe the other input is driving by some other gate. It could be low. Then what is my current here, right? If I'm feeding the gate like this, where both of the inputs are high, then what is my current going into the single input? Now, do you understand when I say worst current requirement, what do I mean by that? Okay. Now let's see IIH case 1.